All right, hello everybody. This is Mr. Santillana, and these are your video notes for our geometry class. Fisher students, note that these are the notes for section 6.1. Topics that we're going to cover are as follow. We're going to be talking about polygons, angle sum theorem, and quadrilaterals. A lot about quadrilaterals. So here we go. All right, make sure that you copy these notes down in your composition book, everybody. And let's start off with the main idea here. What are we going to be looking at? We're going to be looking at three things: measurements, proofs, and coordinate geometry. And as far as measurements are concerned, we're looking at lengths, we're looking at areas, volumes, angle measurements, and units. We still have proofs. The majority of the proofs are going to be around proving whether a quadrilateral is in fact a parallelogram. That's what the proofs will be around. And some of the usual suspects here in coordinate geometry: the distance formula, midpoint formula, and calculating slope. Nothing new there, stuff that you already know. All right, let's start with the theorems here. Or actually, start with quadrilaterals. So we need to know what they are, who they are, and how they relate to one another. So in the family of quadrilaterals, we have polygons that have four sides, right? Well, the first set of categories are as such. We have a kite, we have a parallelogram, and we have a trapezoid. The kite happens to be a category on its own. However, the other two categories, parallelograms and trapezoids, have subsets of each other. For example, a parallelogram, right, has a rhombus and it has a rectangle. A square happens to be a combination of both a rhombus and a rectangle. By the way, a rhombus is also known as a diamond. All right, then we have the trapezoids. And there's only one type of, or one special case for the trapezoids. That's the isosceles trapezoids, where the base angles and the opposite sides here are, in fact, congruent to each other. So there's the family of quadrilaterals. Let's take a look at the theorems now. Okay, first theorem that we're going to study is the polygon angle sum theorem, theorem 6.1, and it reads as follows. The sum of measures of the interior angles of an anagon is n minus 2 times 180. Notice that this formula is used for finding the sum, not each interior angle, the sum of all the interior angles. N stands for any number of sides of the polygon, and an anagon is a polygon with n number of sides. N number of sides, it could be 5 sides, 8 sides, 12 sides, whatever. All right, now we have a corollary to this theorem, 6.1. What if you didn't want the sum of all the interior angles, but the measure of each individual interior angle? Well, in that case, the measure of each interior angle of a regular polygon is, same formula, n minus 2 times 180 divided by n. Okay? Now, you see the word regular polygon here. That's important to point out because a regular polygon is something very particular. It's a polygon that is both equilateral and equiangular. By equilateral, we're talking about every single side is congruent to itself. And equiangular because all of the interior angles are equal to themselves. Let's keep moving on. We have the next theorem, theorem 6.2, the polygon exterior angle sum theorem. You've looked at something like this before, so you're familiar with it. As far as exterior angles are concerned, the sum, again, it's the sum of the measure of the exterior angles of a polygon. And remember, there's always an exterior angle at each vertex on the outside, add up to 360. Here's an example. We have a quadrilateral. All of these exterior angles on the outside add up to 360. All right, let's go ahead and take a look at a common error that I've seen throughout the years with my students. Notice here we have a parallelogram. We have a pair of parallel sides. Typically, my students will also assume right away that both of these sides are congruent. Do not make that mistake. We don't know if the sides are congruent just because they are parallel. That's a common error that I see all the time, year after year, so please don't make it. All right, here's a little hint. In studying parallelograms and quadrilaterals, you really need to be a master of the skills or relationships relating to congruent triangles, parallel lines, and transversals. If you've been able to master these three, really chapters 3, 4, and 5, you'll be okay in this next chapter when we study quadrilaterals and parallelograms. The last thing I want to go over is this idea of a non-overlapping triangles. So we have the sum interior angles formula. It's n minus 2 times 180. Now here we have an octagon. We have a regular octagon, and I've broken it up into triangles. Here, from the center, I am drawing all of my rectangles. And notice that I'm drawing a segment from the center to the vertice. I have a total of 8 triangles. Here, all of my triangles, all 6 of them, stem from one and only one vertice here. So which is the proper way of breaking up your polygons? Well, with regards to this formula, notice if we have an octagon, which we have here, and we have 8 sides, the formula says that you take the 8 sides, you subtract 2 of them. Well, 8 minus 2 is 6. 6 times 180 will give you the sum of all the interior angles. Most kids will break up their polygon this way, and they'll see 8 triangles, and so they will multiply. Well, each triangle has 180 degrees internally, so 180 degrees times 8 gives you all of the internal angles. But notice that you're adding this angle at this corner and the one in the middle, so you can't break it up this way. This is the proper drawing for it. Here you can see that 8 minus 2 is 6, and here are the 6 triangles. You have to break it up by stemming each segment from one vertice. All right? Okay, good luck, and I'll see you next week. Bye-bye.